Alright, so in this video we go over section 2.5, more about limits, and we introduce a new concept which is continuity. In this section we will discuss the different properties of limits that are, like implied every time we evaluate or we compute a limit, some of these properties that are behind every time we compute one of these. And then we will look at limits at of rational functions. And in this case, well, we already looked at some of those, but this time we're gonna look at limits at infinity, by the way, and then identify continuous function and go over the concept of continuity. So what are these properties of limits? Well, so suppose C is just a constant, a multiple, and then there's these two limits, the limit of f of x and the limit of g of x. And well, whatever that limit is, L1 and L2, you can label like that, but don't worry, no, let's not define anything. So in this case, the first property tells us that when we have the limit of a sum of two functions, we can write this as the sum of a limit and of the two limits, and the same applies when we have one of them to be negative when we would have the difference of a limit. The limit of a constant, the limit of just a number, is c times the limit of 1, which is simply that constant. For example, the limit of 4 as x approaches, I don't know, maybe 1, maybe 0. Well, it's just a constant. A constant times a function, when we multiply a constant times a function, we can have the constant outside and then evaluate the limit individually. When we have the limit of a product of two functions, we can evaluate this as the limit at the product of the two limits. And the same applies for when we have, in the situation when we have the limit of a quotient, evaluate each individual limit in the numerator and the denominator. And another next one that we haven't done before is when we have radicals. Well, when you have the limit of a radical function, this limit symbol can go inside of the limit and instead take the square root, or not the square root, but the end root of the limit of the function. And of course, I mean, there's more intuitive properties of limits. For example, when you have the limit of the function e to the f of x, this is the same. Well, x approaches a. This is e to the limit of f of x. You can use this same idea intuitively, and then the limit of a natural log of f of x as x approaches a in the same way. So it's the same as saying the natural log of the limit of the function f of x as x approaches a. I mean, it's the same properties that can be, for which we can extend this to. Well, let's use properties of limits to find, to evaluate the following limit. So in this case, well, so we will use the properties of limits. Of course, every time that we want to evaluate this limit, all we do is simply substitute the value for x and simplify. And if we get one of those indeterminate forms like 0 over 0, well, then we may need to do algebra to simplify this. And otherwise, if it's a number over 0, well, then we may need to study the function that gets related. So for example, here, I'm going to do only one example in which we are going to illustrate the different, properties of limits. And in particular, I'm going to change this limit x approaches 2 of the cube root of the quotient x plus 3 and x plus 6. I'm going to write this in the form of the cube root of the limit of x plus 3 over x plus 6 as x approaches 2. And then furthermore, I'm going to use like the quotient of the limit of a quotient that can be rewritten as the quotient of two limits. In other words, the cube root of the limit as x approaches 3, of x plus 3 as x approaches 2 over the limit of x plus 6 as x approaches 2. And in this case, compute the limit in the numerator. Well, all we do is substitute the 2 wherever we see the letter x. So the cube root of 2 plus 3 over the cube root of 2 plus 6, which in this case, it's going to be, well, 2 plus 3. This will be 5. And 2 plus 6, which is 8. Alright, well, in this case, notice that we can use the quotient rule for radicals, writing the cube root of 5. Make this look nicer. Cube root of 5 over the cube root of 8, and compute the perfect cubes, which in this case is the one in the denominator. That is the cube root of 5. Yeah, that's going to be a funky number. And ultimately, this is the result. This is the final answer. I mean, it's same thing that we did in the first couple of sections, except that we are just, explaining what is really going. We are taking the limit of each individual term, or factor. We're going to look at limits for which piecewise functions exist, are involved rather. So let's recall on the one hand that the limit of a function f of x as x approaches a exists if and only if both limits from either side also are actually the same. They exist and they are both the same. So for example, you might remember the case in which we have this limit for 1 over x and the limit for 1 over x squared, for example. So in this case, we look that when approaching x for 1 over x, when approaching 0 from the left and from the right, we got different values. Both of the limit here disagreed, so the limit was a DNE. All right. However, on the other hand, for the case with 1 over x squared, from either side, notice how the limit is the same to positive infinity, and that's in this case the limit exists. Well, I mean, it's still DNE technically because it's infinity, but it's in this case positive infinity. Now let's see. Let's look at one case in which to determine whether these limits do exist or do not exist. So on the one hand, we need to determine the limit from the left and the limit from the right. So from the left, well, the limit from the left, we're going to use this expression. Notice this piecewise function is defined with two different pieces, and in this case the reference value is x equals to 3. So less than or equal to 3, which is the one I highlighted in green, this is from the left. This is going to go to the left. You can just write left. But otherwise, well, we're going to look at the right afterwards. So what we're going to do is evaluate the limit of f of x as x approaches 3 from the left. That is limit of 2x, in this case, as x approaches 3 from the left. And in this case, well, this is the limit. No more limit symbol here when we plug in the value. So that's going to be 2 times 3, which equals to 6. All right. Now we're going to do the same. We're going to do the same operation here for the right limit. So in this case, now notice x is going to 3 or bigger. That means to the right. And in this case, from the right, we will calculate the limit of f of x as x approaches 3 from the right, and in this case we will use the expression that accounts for values of x greater than 3, that is to the right, which in this case is x plus 3. Approaches 3 from the right, that is 3 plus 3, which reduces to 6. And in this case, well, all we have to do is compare these two values. Did we get the same value, whether from the left or from the right? In this case, limit, our conclusion is that limit as x approaches 3 of f of x equals to 6, because the limit of f of x as x approaches 3 from the left equals the limit f of x as x approaches 3 from the right. This is why the limit exists, because it's the same limit on both sides. Now let's see if it's the same. Let's look at the situation on example 3. So we have a piecewise function for as x equals 2 being our reference value. So in this case, we want to find whether limit x approaches 2 exists. And what we need to do is to find the limit from either side and compare if they are both the same. For example, limit, so from the left, and this will be, which color did I get? Green. Left, and limit f of x, x approaches 2 from the left, that is, will correspond to the limit of 4x squared minus 1 as x approaches 2 from the left, which equals 4 times 2 squared minus 1, which reduces, okay, so 2 squared, which is 4 times 4 equals to 16. 16 minus 1 is 15. So that's the limit from the left. Let's see what happens from the right. So from the right, limit x approaches 2 from the right, f of x, limit of negative 2x minus 5 as x approaches 2 from the right, and in this case from the right because we are looking at this part of the limit right here. All right. To the right. So let's compute the limit. Well, all we do is negative 2 times 2 minus 5, which is going to give us of negative 4 minus 5, that's a negative 9. Now in this case, if you compare these two limits from either side, they are not the same value. They're not the same. So our conclusion is that limit of f of x as x approaches to plain vanilla 2 equals d and e. And this is because in this case, limit of f of x as x approaches to from the left is not the same as the limit of f of x as x approaches to from the right. So for this reason, in this case, that's why the limit is at the end. Okay. Now let's move on to the next topic, which is evaluating limits involving rational functions at plus or minus infinity. Right? At plus or minus infinity. Well, let's recall first of all that a rational function is a function of the form f of x. F of x equals to p of x over q of x, where q of x, both p and q of x are polynomial functions, and q of x is not zero, because if q of x is zero, well, I mean, divide a quantity over zero is to you're gonna be left to an undefined quantity. Now, the general strategy to evaluate or to compute this limit is to divide each term that is present on the expression by the highest power of x present in the function. All right, so let's see. Let's look at a couple of examples. So number one, so let's identify the highest power for this limit x approaches infinity of 3x over 5, 3x over 5 over 2x plus minus, or rather minus 1. So in this case, the highest power of x is x to the first power. So this will be limit of 3x plus 5 2x minus 1, and we are going to divide all of this by x, which is the highest power of x present in the limit as x approaches infinity. Well, when we simplify this to the following: limit 3x over x, see how these x's go away, and we are left with 3 plus 5 over x divided by 2 minus 1 over x as x approaches infinity. Now, in this case, what is going to happen when these terms go to infinity? Well, when you divide 5 by infinity, so you're dividing a number by an infinitely large number, eventually getting a 0 here and a 0 there. And the terms that survive here are going to be 3 halves, and that's the limit. Of course, we are going to discuss, and that's why I have extra space here, because I'm going to backtrack to these examples when we finish this. Okay, what's the limit of 2x plus 3 over x cubed minus 8 as x approaches infinity? I know maybe you are thinking of factoring that difference of cubes in the denominator, but I mean, in this case, we are not going to be able to cancel anything. So in this case, let's divide by the highest power of x, and in this case, the highest power of x is, in this case, x cubed. So we are going to divide by every single term by the highest power of x, which is x to the third power. So divide by x cubed, divide by x cubed, divide by x cubed, divide by x cubed. All right, as x approaches infinity. Well, so 2x over x cubed, that's going to give us, okay, first of all, the limit 2 over x squared plus 3 over x cubed, and in the denominator x cubed over x cubed, that's going to be 1 minus 8 over x cubed as x approaches infinity. Well, let's evaluate every single term. So 2 over a big number will be 0. 3 over a big number will be 0. Well, I mean, 2 over x squared, that is 2 over infinity squared. If infinity is already big, now imagine infinity squared. That's way bigger, a way bigger number, so that's still 0. This is also 0, and we will be left with a 0 in the numerator over 1, which equals to 0, and that is our limit here. Let's look at letter C. Letter C, well, we have this ugly looking polynomial in the numerator, and that is x cubed plus x squared minus x plus 1 over x squared minus 4. So we'll use the same general strategy, which is to divide every single term by the highest power that you see of x. And in this case, the highest power again is the third power. So x cubed over over plus x squared over minus x over plus 1 over, and then divided by x squared minus 4, and in this case each term divide by x cubed. Well, let's see what we're gonna get when we simplify all this. Let's see. So by simplifying all this, we get that limit x cubed over x cubed is 1 plus 1 over x plus 1 over x squared plus 1 over x cubed. Whole thing divided by x squared over x cubed, which is 1 over x minus 4 over x cubed as x approaches negative infinity. Okay. So in this case, well, this will be 0, 0, 0, 0, and 0. So what are we going to get in this case? And well, this is where these kind of limits are going to get a little bit tricky. So we get 1 over 0, which is the c over 0 form that we discussed in the first section in the class when we cover limits. Well, so this is very similar to studying the function f of x equals 1 over x, where x equals as x approaches 0. But in this case, are we approaching from the left or from the right? Well, it's got to do with the sign of the infinity or where the infinity is going to. However, this may be a little bit tricky. So let's stop this for now and look at the summary that we have here. And this summary right here might be very, very reminiscent of what you did in college algebra. When you have a polynomial function of the form, again, I'm repeating this, p of x over q of x, but I'm giving them a better identity to each, to each polynomial here. These are polynomials with preferably integer coefficients, or could be fractions, that's fine. So, and this you cover back in college algebra as the horizontal asymptotes of the rational function. Those horizontal asymptotes are pretty much the behavior when as x approaches infinity. You may have touched base with the concept of limit at infinity back when you cover this kind of asymptote, and that's what these horizontal asymptotes are, the tendency as x approaches infinity. And well, when you have polynomial over polynomial functions, all you have to do, case one, look at the coefficients, the leading coefficients, a of n and b of n. Okay, so we have so if or right, no, not the coefficients, rather it's the degrees of the coefficient. So degree n and degree m. Okay, so degree n over degree m. All right, so when you look at these polynomials and the degrees of the numerator and the denominator are the same, all you have to do is look at the ratio of the leading coefficient, and that's your limit. When the degree of the denominator is larger than the degree of the numerator, in this case the limit is 0. And last but not least, when the degree of the denominator is smaller than the degree of the numerator, well, this limit could be either positive infinity or negative infinity, depending on the signs of a sub n and b sub n. So in this third case, we are going to use it to answer the third question. So let's go back to the original limit. So rather than dividing every single term by the highest power of x that is present in the expression, we can use that. Well, it's not necessarily a shortcut, but these are like good results. And in this case, well, what do we have? Degree 1, and in this case, m equals to n. The degrees of the numerator and the denominator are the same. All we do is simply the ratio of the leading coefficients, which is 3/2. That's it. And it's consistent with what we got over here. Let's do letter B. So for letter B, we have the degree of the denominator to be less than the degree of the numerator, all right? Because in this case, this is 1 and this is 3. Okay, it's larger. For this reason, all you have to do is, the result is 0, which is consistent with this. Wait, well, why is that just a 0? Well, look at the degree of the denominator. The degree of the denominator is bigger. That means that the infinity in the denominator is way bigger than the one in the numerator. So you are still dividing by a larger number in the denominator. So when you divide by a larger number in the denominator, you are still going to get 0. Now, for this case, well, did I word it? Oh no, that's supposed to be m greater than. I was this is supposed to be the other way around. It is like this. Okay, so denominator larger than the numerator. For in this case, we have the case for which the denominator degree is less than the degree in the numerator. And in this case, well, in this case, we need to determine whether this is positive or negative infinity. Well, in this case, it's going to be negative infinity because, well, so suppose another way to look at this one is to neglect the lower degree terms. Neglect all these terms, right? Just call it a day for those terms and focus only with the leading terms. So what I'm going to do here is find the limit as x approaches negative infinity of x cubed over x squared. And that's going to be the limit of simply x as x approaches negative infinity. Plugging in, what are we going to get? Negative infinity. So that's another good strategy to evaluate this kind of limit. So because again, I agree that it might be a little bit tedious to divide by the highest power of x present in the limit expression. Yes, in some cases you may be required. For example, if we were in taking this class in person, I might ask at least one or a couple of examples in which I would ask you to show how you get that limit by dividing by the highest power that it's present. But I mean, in this case, you can just go and use whatever strategy works best for you. And well, now that we cover limits at infinity, we will discuss one last topic, which is the concept of continuity. And well, a function y equals f of x is said to be continuous at x equals a if all of the following conditions are met or are true. Number one, f evaluated at a is defined. Well, by the way, this is where I differ with the textbook. The textbook says f of a exists. Recall that limits exist or do not exist, as opposed to functions that are defined or not or undefined. And then the limit, plain vanilla limit, exists. That is, the limit from both sides of a exists. And the third condition is that it's a consequence of or a combination of the first and the second one. That is, that the limit of f of x as x approaches a is exactly f evaluated at a. And we're going to look at an example to use the definition of continuity to determine whether the function f of x equals x squared minus x minus 6 over x minus 3 is continuous at x equals to 2 and at x equals to 3. So, and I have the graph over here, the graph of this rational function. Notice it looks like linear You'll see why in a second. And of course, I mean, this is something you may have seen in college algebra. Why do you get linear functions when you have these weird looking, functions, right? So number one, want to do for x equals to 2. Number one, let's evaluate f of 2. So number one, so that's a 2 squared minus 2 minus 6 over 2 minus 3. So in this case, we're going to get 2 squared, which is 4, minus 2, which is 2. 2 minus 6, which is a negative 4 in the numerator, and negative 1 in the denominator, and actually the function is defined. So far so good. We checked one of the first conditions. So number one, let's check. Okay, let me list the first condition, the second condition. Is the limit of x squared minus x minus 6 over x minus 3 as x approaches 2. Does the limit exist? Well, let's see. Notice this is very the same as evaluating the function. So what do we do every time we evaluate a function? Substitute. No, not evaluating a function, computing a limit, evaluating a limit it's exactly the same way as evaluating a function. However, the concept behind is different, and well, it's the same value. So when we compare this to 1 with 2, for number 3, for the third condition, we need to compare whether limit of f of x as x approaches 2 is equal to f of 2. And for this reason, this is good, these two quantities are the same, 4 and 4, and for this reason, we can conclude at the end that f of x is continuous at x equals to 2. And we can see that in the graph, so the moment we evaluated f of 2 to be equal to 4, well, that's this order pair here. And well, so that's the order pair. Notice we have a solid bubble. The function is defined. That means we can step on that point. Now, looking at the limit from the right rather, and from the left, actually, let me use something different. So from the left, the limit is the same as coming from the right. It's the same y value. All right. Now let's find out whether, number one, for whether this is the function is continuous at x equals to 3. So in this case, for x equals to 3, so for x equals to 3, limit, well, the number one condition, not even the limit, it's just evaluate the function at 3. That is 3 squared minus 3 minus 6 and divided by 3 minus 3. Well, in the denominator, right away we get a 0. And then in the numerator we get 3 squared, which is 6. And then 3 squared, which is 9, not 6, my bad. 9 minus 3, which is 6. Minus 6, it's also 0. So in this case, this means undefined. The function is undefined. So in this case, the first condition is not met. The function is not defined at that value. Even though if we perform the limit will exist anyway. The limit will exist because if we look at the graph coming from the left and coming from the right, the limit is still the same. However, because the function is not defined, then the function f of x is not continuous at x equals to 3. Alright, so how come? Well, you can think of continuity as the ability to draw the graph of a function without ever lifting our pencil. For example, if I do this here, there's this hole right here for which that I have to jump in order to keep drawing the graph of the function. So, and well, that hole in there is the reason for which this function is not continuous, right? So, oops, erase all this. Let's look at other examples. So, for the next example, we need to have a precise definition of the absolute value function. So the absolute value function f of x equals, well, absolute value bars of x. This can be really defined in the form of a piecewise defined function. For example, let me draw the graph of, it's the v shape. That is correct if you were thinking of that function. Yes, it's the v shape. And well, so for negative values, for values to the left of x equals to 0, that is -1, -2, -3, we have the graph of negative x with a negative slope. And otherwise, for positive values of x, we have the diagonal line with positive, with positive slope. That's how we define piecewise. But a more generalized form, for example, if you have more in general, if you have this shifted function, this graph of absolute value, shifted a units for now, let me just take the case when it's shifted to, when the graph is shifted to the right, and this is shifted a units. So we are going to have, and this will have a y-intercept at a. So for positive values greater than a, we are going to have x minus a, having this line with positive slope. But on the other hand, negative x minus a for negative values, or rather, not negative, rather values to the left of a, which is where the cusp of the graph of the absolute value function is at. And we're going to use this piece of information to determine whether the function f of x equals x minus 4 over the absolute value of x minus 4 is continuous. So let's see. So something very interesting is going to happen this time. So number one, the first condition is to evaluate the function at 4. So 4 minus 4 over the absolute value of 4 minus 4. All right. And well, what are we going to get in this case? Well, 4 minus 4, well, and that's a 0, essentially 0 over 0. And well, in this case, well, that's the function is not defined, therefore the function is not continuous. However, we may need a more rigorous way to show this by computing the limits. Notice, I'm going to do part 2. Does the limit exist? Well, number one, so we need to find limit of x minus 4 over the absolute value of x minus 4 as x approaches 4 from the left, and limit x approaches 4 from the right of the same. Now, from the definition of the absolute value function, from the left, I'm going to replace the absolute value bars with a negative in the front and parentheses around the expression. Oops. And well, in this case, when we simplify this, x minus 4 over x minus 4, what do we get? Essentially 1 over negative 1, which is negative 1. For the case in which x approaches 4 from the right, we simply get rid of the values of the absolute value bars. And this is also equal to 1. Now, the problem here is that these two limits right here, when we compare them, these two limits disagree. For this reason, limit as x approaches 4, plain vanilla 4, not from the left, not from the left, and not from the right. Actually, plain vanilla 4, and in this case, of f of x, d and e. The reason for this is because those two limits disagree. Again, same idea. And a very classical problem in continuity is that you are given a piecewise defined function, you know, like x squared if x is less than 2, you know, and I'm gonna highlight. Notice it's the parabola, but it's not the entire parabola. It's rather just the portion of the parabola with x values that are less than 2. And then we have this kind of funky looking function, negative 3x plus k. Well, it's a linear function with negative slope. So what they're asking us to do is to find the value of k. Find the value of k so that f of x will be continuous at x equals to 2. And all we have to do is, well, I mean, trial and error definitely not going to work. So we may need to have an equation. We will solve a system of equations rather for which, you know, we can set these two equations equal to each other. That is, they intersect at a point, you know, because I mean, if for some reason, well, let's just do the following. Let's just do x squared equals to negative 3x plus k, and then for x equals to 2, because that's what we want to obtain, we want to force these two functions to intersect at x equals 2. So plug in at 2 wherever you see the letter x. So that's going to be 4 equals negative 6 plus k, you know, and in this case k, solving for k equals to 10. So that is, if the function is f of x equals negative 3x plus 10, this is the case in which, well, let's keep finding the intercept, the y-intercept at 10. That's what makes the function or this piecewise function to be continuous. For example, if k were 9, well, this line would have been shifted down 1 unit and have a like this and have a jump discontinuity, and in this case, well, the function would not be continuous. All right, so this was this is a very classical problem in calculus, in continuity. There's another point of view to look at this problem, you know, thinking of it in terms of limits, like limit of f of x from x approaches 2 from the left has to be also equal to the limit of f of x as x approaches 2 from the right. And of course, from the left we have the quantity limit x squared as x approaches 2 from the left, and limit negative 3x plus k as x approaches 2 from the right. But of course, when we evaluate these limits for x, it is the same as doing all this that we got here. All right, so either point of view is fine. All right, so I think this is a good place to quit. I'll see you in the next video.